So here's the agenda for today's class. Again, I didn't have time to do Mightiest Points credits last class. There aren't any Mightiest Points. I'll definitely remember to do some today, and we'll have to go over them in the next class. I've got to finish off section 7.7, so we'll be doing 7.7.2. I'm going to do the rest of section 7.7, and then I'm going to be covering section 7.8 today. I've divided 7.8 into two halves, 7.8.1, 7.8.2. I should be doing the first half before the break, the second half after the break. I did bring the quizzes today, so I do have the quizzes from a week and a half ago to hand back. Yes?
What chapter is the quiz?
Quiz today is everything since the last quiz in chapter 7. So 7.4, 7.5, 7.7, 7.8. And I did mention that last Thursday's class as well. The reason I'm putting so much on it is because this is the last chance you're going to get something back before the next midterm. So I want to put more on it because it means that you'll have more of a chance of getting feedback before the midterm. So again, the quizzes are not worth a ton of marks, and I do put more on them specifically so that I can give you feedback on those topics for the midterm. So again, looking at how well you do in the quiz is hopefully going to help you study for the next midterm. If I don't finish 7.8.2, it'll just be on 7.8.1. It won't be on 7.8.2. But I'm pretty confident I can get through all of it today. Other thing I'm going to mention, I'm going to do this. Actually, I'll do it now. I don't know why I decided to wait for them. The date for the final exam, I haven't mentioned it in class yet. I've mentioned it to a couple of people. It's been a month since it was posted online, but people have asked for it after class, and I've told people, but I'm just going to go to the final exam schedule. Where's my exam schedule? Why am I having a hard time? Semester info, exam schedules. There we go. View exam schedule. So if you look at, and this is what I wanted to look this up because I don't remember the room number. There we go. So the exam is on August 8th. It's from 2 p.m. to 5 p.m. And it is in room B132. So again, I will probably close to the exam date announce that room again, but the key thing you need to know is August 8th, which is a Friday, I believe. So the last day of class is on the Tuesday of that week. That last day is going to be a review day. The Friday of that week is the actual exam. Okay. Okay, it looks like it's recording, which is good. Okay. So, any questions before I move on to finish section 7.7?
No.
Okay. So just as a review, last class I talked about two methods for finding approximate integrals, and they're called the midpoint rule and the trapezoid rule. I went over one example of the midpoint rule, one example of the trapezoid rule, sort of comparing the results you get from the two, talking about whether the results an overestimate or an underestimate. And I'm going to do one more example before I move on, just to sort of review the midpoint rule and the trapezoid rule. So, the idea here is what we use the midpoint rule and the trapezoid rule for is to approximate integrals that we can't evaluate. There are integrals out there that we cannot evaluate, and the midpoint rule and trapezoid rule are useful for approximating those. I realized I just had a quick peek at my notes, and the notes I did for class, I copied down this x to 6 as an x squared. So I'm going to do that one because that's the one I've done calculations already for. It works just as well with x to the 6. But I'm going to do it with x squared because this morning when I was pre-computing things, I read that as a 2 rather than a 6. I don't know why. Anyways, so if you want to approximate this integral, this integral actually turns out to be one you can evaluate. So this would have been a silly example. But anyways, if it was an x to the 6, you'd do the same thing just with a 6th power instead of a square. Now, if you want to approximate it, I'm going to use the trapezoidal rule and the midpoint rule. Okay? So there's an AP missing there. Anyways, so the idea is the trapezoid rule says that you do is you take the interval from 0 to 2, right? You divide it up into 8 pieces, because it's n equals 8, right? So divide it in half, puts it here. Divide it in half again, there's a 0.5 and a 1.5. That's dividing it into 4 pieces. If you divide it into 8 pieces, you have a 0.25, 0.75, 1.25, 1.75. And the trapezoid rule says you take the first one once, the last one once. Oh boy, that's not working very well. Take the first one once, the last one once, all the middle ones I take 2 times. Right? Trapezoid rule, that's what trapezoid rule says, is you always pick the first one once, last one once, middle ones all 2 times. So the approximation is going to look like delta x over 2, right? Now the delta x here is 0.25. That's the length of these intervals is 0.25. Again, remember the formula for delta x is always b minus a over n. And we're going to have 1 times this thing when I plug in 0. Plus 2 times this thing when I plug in 0.25. Plus 2 times this thing when I plug in 0.5. Plus 2 times this thing when I plug in 0.75. Plus, and again it's going to have to keep going, 2 times this thing when I plug in 1. Oh, sorry, that's times 2 times what I get when I plug in 1.25. 2 times what I get when I plug in 1.5, 2 times what I get when I plug in 1.75, and then the last one when I plug in 2, I'm only taking that once, right? So the first one I take once, the last one I take once, all the other ones I take twice when I'm using the trapezoid rule. And again, what I'm taking is I'm taking the value of the function at that point. I'm taking these numbers that I've used to divide up that interval from 0 to 2 and plugging them into the function. And if I do this calculation, the number I get, this is T8, the trapezoid rule with 8 subintervals, is approximately 1.106. So when I do the calculation with this function, 1 over 1 plus x squared, using 8 subintervals, the trapezoid rule, that's the result I get. Any questions about how I came up with this formula, how I came up with what delta x is, those sorts of things? Now I could do the same thing with the midpoint rule. Now when I use the midpoint rule, rather than taking these numbers, which I've already found, I'm going to take the midpoint of each of those subintervals. So here, the midpoint is 0.125. It's halfway between 0 and 0.25. Here, the midpoint is 0.375. Here, the midpoint is 0.625. Here, the midpoint is 0.875. Here, now this is where I'm running out of space, the midpoint is 1.125. Here, the midpoint is 1.375. Here, the midpoint is 1.625. And the last midpoint is 1.875. So again, rather than using those numbers I've already found, which are the endpoints of subintervals, let me pick the midpoint of each subinterval. And when I use the midpoint rule, I use each of them once. So here, rather than delta x over 2, when I use the midpoint rule, it's just delta x. And when I use the midpoint rule, I'm not going to have any of these 2's. Right, I'm only going to be using everything once. And the other thing that's going to change are these numbers. The first number with the midpoint rule will be 0.125. The second number will be 0.375. The third number will be 625. The fourth number will be 875. The fifth one will be 1.125. The sixth one will be 1.375. The seventh one will be 1.625. And the last one will be 1.875. Now, one thing to mention, when I used the trapezoid rule, I had n equals 8, but I had 9 different numbers. Whereas when I use the midpoint rule, I only have 8 different numbers that I'm plugging in. The reason is because when I use the trapezoid rule, I'm counting both the beginning one and the ending one. Right? So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, even though there's only 8 intervals. That's because I'm using for both the beginning and the end, as well as all the 7 dividing lines. Whereas when I use the midpoint rule, I'm only using 8 numbers. So if I do this calculation, the number I get from the midpoint rule is 1.107. So you'll see these two numbers are fairly close together. And that's what should be expected. If you do everything correctly, the numbers you get from just different estimates should be fairly close together, because they should be fairly close to the actual value of this integral. Any questions about how I do the trapezoid rule or the midpoint rule here? Okay. There's one last rule that we're going to use to approximate integrals, and it's called Simpson's rule. Simpson's rule turns out to give better approximations than either the trapezoid rule or the midpoint rule. When you're using Simpson's rule, rather than approximating something using rectangles or trapezoids, you're actually using parabolas. So if you have a function like this, and let's say we divide it up into pieces like this, then here, what you're going to do is you're going to draw a parabola that looks like this. Here we draw a parabola that looks like this. Here you draw a parabola that looks like this. Here you draw a parabola that looks like this. And the idea is parabolas, since they can be curved, can approximate the curve a lot better than rectangles can. Now the annoying thing is that to draw a parabola, you can't just use 2 points. To actually make the parabola fit the curve, you have to actually pick a point in between. So when we're drawing parabolas, you're actually, if n is 8, so if you divide this up into 8 pieces, 1, 2, 3, 4, 5, 6, 7, 8, you're actually only going to have 4 separate parabolas. The formula for the area of a parabola turns out to be this guy. You don't really need to know the formula for the area of a parabola if you don't want to, but basically that is the formula for the area of a parabola. What's really more important is the formula for Simpson's rule. The formula for Simpson's rule says this. The first point that you've measured the height at, you're going to take once. The second one you're going to take 4 times. The third one you're going to take 2 times. Fourth one you're going to take 4 times. This one you're going to take 2 times. This one you're going to take 4 times. This one you're going to take 2 times. This one you're going to take 4 times. And the last one you're going to take only once. So the pattern for Simpson's rule is 1, 4, 2, 4, 2, 4, 2, 4, 1. And that pattern turns out to give you parabolas which approximate the curve pretty darn well. When you use these parabolas, you also have to multiply by delta x over 3. This delta x over 3 turns out to come from the formula for the area of a parabola, if you're interested. Now, you can find, again, if you look through the textbook, it'll tell you where that formula for the area of a parabola comes from. For this point, all you really need to know are the numbers for Simpson's rule. The 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Right? Put as many 2, 4s in as you need to actually fit the pattern. One thing to mention about Simpson's rule, it'll only work if the number of rectangles, or if the number of subintervals is even. So you can't do Simpson's rule with n equals 5 or with n equals 11. You can only do it with an even number, like n equals 8, n equals 10, n equals 12. In that case, you can actually fit all the numbers in. So, to do an example, I'm going to use Simpson's rule to approximate this integral. Integral from 0 to 1, square root of z, e to the negative z, dz. And here we're using n equals 10. What that means that we're using n equals 10 is that we've got the interval from 0 to 1, and we're going to cut it into 10 pieces. So if we cut it in half, that gives you 0.5. I've got to cut each of these halves into 5 pieces. So this one will be at 0.1, 0.2, 0.3, 0.4. That's 1, 2, 3, 4, 5 pieces. This side's going to be cut at 0.6, 0.7, 0.8, and 0.9. Now the Simpsons rule pattern, so they use the first number once, second number 2 times, third number 4, 1, 4, sorry. 1, 4, 2, 4, 2, 4, 2, 4, 2, 1. So, when I set up the formula for Simpson's rule, I'm going to have a delta x over 3. Delta x here is 0.1. I'm going to have a 0.1 over 3.
Is that 4 and 1? 4, 2,
Oh.
4, 1?
Thank you. Thank you. Yes. It should always end with 4, 1. I don't know why I got a 2, 1 there. I think because I forgot about the last one here. Anyways, so we're going to evaluate at 0, and we're going to do that once. So we're going to have a square root of 0 e to the negative 0. That's the first one. Here, I'm going to have it 4 times, and it's going to be evaluated at 0.1. So we have square root of 0.1 e to the negative 0.1. The next one happens 2 times, and it's at 0.2. The next one happens 4 times, and it's at 0.3. The next one happens 2 times, and it's at 0.4. The next one happens 4 times, so 4 square root of 0.5 e to the negative 0.5. Next one happens 2 times. Next one happens 4 times. Wait, 7. Then we've got one that happens 2 times, which is 0.8. Then we've got one that happens 4 times, which is 0.9. And the last one only happens once. And the last one's going to be square root of 1 e to the negative 1. So the Simpsons rule, like approximation for this, will be 0.1 over 3 in front. Always starts with delta x over 3. Here we have 1 square root of 0 e to the negative 0. 4 square root of 0.1 e to the negative 0.1. 2 square root of 0.2 e to the negative 0.2. 4 square root of 0.3 e to the negative 0.3. 2 square root of 0.4 e to the negative 0.4, etc. And if you complete this calculation, the number you get from this, which is called S10, is the approximation using Simpson's rule, and n equals 10, gives you 0.376. So you'll notice, yeah. Anyways, I was going to say, this is an example of something you can't integrate, so I can't actually compare this to what the integral was to say how accurate or how not accurate it was. But this is what you get out of Simpson's rule here. Any questions about this example before I move to the next one? So the last example I'm going to do is one where I'm going to compare Simpson's rule to the midpoint rule. So Simpson's rule is this 1, 4, 2, 4, 2, 4, 2, 4, 1 pattern. Again, it seems a little bit more complicated than either the midpoint rule or the trapezoid rule. That's because of that weird pattern that's going on. The calculations aren't really any more complicated. You still have a long string of numbers that are each, evaluated in the function multiplied by something. But the pattern's a little bit more complicated. So the question was, does it actually give a better estimate? What I'm going to do is I'm going to work with an integral we can evaluate, estimate it using the midpoint rule, estimate using Simpson's rule, compare what the error is, compare how much each of those are off by, and see what it should be. So here we're going to use the midpoint rule and Simpson's rule with n equals 4 to approximate the value of that integral. Here the integral is the integral from 0 to pi, x cos x dx. Now I'm using n equals 4 just to make the computations simpler here. So here I'm doing n equals 4. The integral is going to be from 0 to pi. Oh, 0 to pi. So if I cut it in half, I'm cutting it at pi over 2. Cut it in half again. This is at pi over 4. This is at 3 pi over 4. So those are my integrals. Now if I'm using the midpoint rule, I'm going to use the midpoints of each of these. This is pi over 8. This turns out to be 3 pi over 8. This turns out to be 5 pi over 8. This turns out to be 7 pi over 8. Basically, I'm just asking what's halfway between 0 and a quarter. It's an 8. So halfway between 0 and pi over 4 is pi over 8, etc. So here I'm going to do the computations for both Simpson's rule and for the midpoint rule. The other thing I'm going to mention is that the delta x here is pi over 4. The length of an interval is pi over 4. So, if I use the midpoint rule, I'm going to have the delta x times, plug this midpoint into the function. So when I plug that in, I get pi over 8 cosine pi over 8. Plug this midpoint in. I get 3 pi over 8 cosine 3 pi over 8. Plug the next one in. I get 5 pi over 8 cosine 5 pi over 8. And the last one's going to be 7 pi over 8 cosine 7 pi over 8. So I take each of those midpoints, I plug it in, add them all up, multiply by delta x. Right? That's the midpoint rule. That's what we're doing when we're using rectangles with their midpoints. When I do that, the answer I get is, I've got this written down here, negative 1.945. Now if I use Simpson's rule, I take the delta x over 3, and when I use Simpson's rule, I'm going to use the green numbers, but I'm going to use them in that 1, 4, 2, 4, 1 pattern. So I'm going to have 0 cosine 0 plus pi over 4 cosine pi over 4. Oh, plus 4 times that, plus 2 times pi over 2 cosine pi over 2, plus 4 times 3 pi over 4 cosine 3 pi over 4, plus 1 times pi cosine pi. Right, so that's what I get from Simpson's rule. I put in 0 for the first one, pi over 4, pi over 2, 3 pi over 4, and pi. And each time the pattern is multiply the first one by 1, second one by 4, third one by 2, third one by 2, fourth one by 4, fifth one by 1. 1, 4, 2, 4, 1 is the pattern here. And the number I get out of that, if I do the calculation, is negative 1.985. So now what I want to do is I want to compare those two numbers, those two approximations, to the actual value of the integral. So I'm going to integrate this thing over here. So if I integrate this, I'm going to choose integration by parts. The x is something I can differentiate. So my u here is going to be x. My dv is going to be the cos x. The du is just going to be dx. The v is going to be sine x. So I'm going to do u times v minus the integral of v du. So u times v is x times sine x minus the integral of sine x dx. Now, I've got to put those limits of integration on. So I put the integral from 0 to pi here, and put the integral from 0 to pi there. Here, x sine x from 0 to pi is pi sine pi minus 0 sine 0. Here, the integral of sine x is negative cos x. Now, it turns out that sine pi and sine 0 are both 0. So this first part here is all 0. So here, these two negatives will become a positive. So really all I'm going to have is cosine pi minus cosine 0. Cosine pi turns out to be negative 1. Cosine 0 is 1. So the exact value of the integral turns out to be negative 2 in this case. So if you look at these two numbers, negative 1.945 and negative 1.5985, they're both pretty close to negative 2, right? But this is the better approximation. Simpson's rule gives you something closer to negative 2 than this one does. This one, the error is 0.155. If I take the estimate minus negative 2, the estimate minus the actual value, oh, 0, there's a 0. No, 0.0055. There we go. Here, if I calculate the error, here the error is 0.015. So again, this error is about a quarter as much as this error, right? The error in Simpson's rule is only a quarter of the error in the midpoint rule. And again, Simpson's rule is a little bit more complicated calculation to do, because you've got to do that 1, 4, 2, 4, 2, 4 pattern. But it turns out to give you better results. By the way, I remember last class, I think it was Daryl asked me about whether or not you can use a graphing calculator to do this. It turns out there are graphing calculator programs out there that will do these calculations for you. And if you're worried about making mistakes in these calculations when you enter them by hand, it might be a good idea to get one of those programs. You can either download them and copy them over via a link table, or you can type it in yourself. One thing I want to see, though, is if you're doing a question like this on the test or on the quiz, I want you to write this out. Even if you're using your calculator to do all the steps, I want you to write out what is the formula that the calculator is doing, just so I can see that you know what the rule is. That it's not just simply, I'm going to tell my calculator to do midpoint rule, so it'll do midpoint rule. I want you to show me that you understand what the midpoint rule is before giving your final answer. But if you want to program your calculator to do that for you, that's totally fine to get the answer. I just want you to show me what the actual formula is first. Any questions about this example 6 here? Again, this should be, section 7.7 should be the easiest thing in chapter 7 so far, because really all you need to know is to know the patterns for the different rules. To know what it means to do the midpoint rule, what it means to do the trapezoid rule, what it means to do Simpson's rule. There's some stuff in section 7.7 about estimating what the error is going to be if you don't know what the actual value is, which I'm not going to cover. And the reason is because it's not that practically useful. And it's a really annoying computations to do. And yeah. So any questions before we move on to section 7.8? Okay. So the last thing in chapter 7, section 7.8, deals with what are called improper integrals. Now, improper integrals are integrals which look like they should be infinitely large. And some of them turn out to actually be infinitely large, some of them turn out to not actually be infinitely large. And I think there was one case I mentioned earlier. I'm not sure if I mentioned this, but I'm just going to mention it now, just to remind everyone of this, if they haven't seen it before. And that is the fact that the fundamental theorem of calculus part 2, that thing that says that you can do integrals using analytic derivatives, it only works if the function is continuous. So for example, if I had this, the integral from -1 to 1 of what, actually I'm going to do 1 over x. Let me just think 1 over x does turn out to actually work out. So I'm going to do 1 over x squared dx. Oh, what was the, no, it was, this is where I should have come up with this example ahead of time.
Are you trying to think of like Gabriel's born? Or?
No, I'm trying to think of an integral which if you do it by looking at the picture and you do it by doing it, you fundamentally calculus 2, you get different results. I may need to come back on it. But the point is, if I did do this integral, and I tried to say, okay, the antiderivative is ln of the absolute value of x, I've got to go from negative 1 to 1, so it's going to be ln1 minus ln absolute value of negative 1, which is ln1 minus ln1, which gives you 0, right? Now if I actually, this is 1, and this was the reason that this example is a bad one to pick, that answer actually turns out to, well, it's not actually correct. It looks, but if you look at the picture, so if you look at the picture of this guy, you're integrating this thing from negative 1 to 1. And so it looks like this area here and this area here should cancel each other out. So it looks like this integral should be 0. I was trying to come up with one where if you looked at the picture, you'd be able to tell that this answer was incorrect. But it turns out this answer is actually incorrect. And the reason this answer is incorrect is because the rule that we're using to do integrals, the fact that you can use antiderivatives to do integrals only works if the function is continuous. This function is not continuous. It jumps from negative infinity up to positive infinity. You can't do that and be a continuous function. So if you have a function like this that's not continuous, you cannot just do antiderivatives to get integrals. And improper integrals is the technique we're going to need to deal with those sorts of functions that are not continuous. Before I talk about ones that are not continuous, I'm going to talk about what I call infinite integrals. So if we have an integral from 1 to infinity of something, how do we deal with that? That's what I'm going to talk about first, partly because it's a little bit easier to wrap your head around than the discontinuous ones are. By the way, does anyone, I mean, there might be some people who take the course before, does anyone feel like they know how they would approach a problem like this? Yes?
Try and use root sum and use it in infinite sum?
That's a really good, that is a good approach, especially if, now it turns out there's a much easier way of doing it than that, but yes, that could. So one thing you can do is if you use Riemann sum on this thing, if you write this as Riemann sum, it'll have, if you pick a certain delta x, you'll have an infinite number of subintervals. And sometimes, as we will learn in chapter 11, some infinite sums converge and some diverge. And so sometimes you can get a limit out of those things. It turns out that is a good approach. It's not the easiest approach. Riemann sums are always sort of the longest way to deal with things. And the key thing is, if you ever see an infinity somewhere, think of it as a limit. That's the idea here. This is the reason, one of the big reasons we covered limits back in beginning of Calculus 1 is because it's really the only way mathematicians have of dealing with infinities. Infinity is not a number, but you can let numbers go to infinity. And that's the idea here, is you have to use limits. So the approach I'm going to use, I'm going to talk about this integral here, integral from 1 to infinity of x to the negative 2. And if you sketch the graph of x to the negative 2, it looks something like this. And when you talk about the integral from 1 to infinity, what you're talking about is this area there. The area under the graph from 1 as far as you can to the right. Now if you look at this area has an infinite width, right? So your thought might be this is an infinite area, right? If you integrate from 1 to infinity, the answer should be infinity. This area is infinitely big. It turns out it's not actually infinitely big. And the way to see this is to do a couple things in turn. First, I'm going to integrate from 1 to 10. See how big that area is. Then I'm going to integrate from 1 to 100. See how big that area is. Then I'm going to integrate from 1 to 1,000. See how big that area is. And you'll notice that these areas are not getting very much bigger when you integrate with bigger numbers. So, if you integrate from 1 to 10, x to the negative 2 dx, the antiderivative of x to the negative 2 is x to the negative 1 over negative 1. We've got to do this from 1 to 10. So it's going to be 10 to the negative 1 over negative 1 minus 1 to the negative 1 over negative 1. 10 to the negative 1 over negative 1 is negative a tenth. This thing is plus 1. Negative a tenth plus 1 is 0.9. Now, if we do the same process with the integral from 1 to 100, the only thing that's going to really change is that this 10 here is going to become 100. So we'll have negative 1 over 100 plus 1, which gives you 0.99. Again, the antiderivative is still going to be the same. We're just going to plug in 100 instead of the 10, which means that this 10 will turn into 100. If we go from 1 to 1,000, again, the same process is going to happen. It's going to have the same antiderivative, but it's going to be negative 1 over 1,000 plus 1. That gives you 0.999. So we can see that each time we add an extra 0 on the limit of integration, as we go farther and farther out along the number line, all we're doing is adding 9s to the end of this thing. So really, if we go infinitely far around along the number line, really all we should be doing is adding an infinite number of 9s. And if we do that, we're basically just going to get 1. Right? As this number, this upper limit goes to infinity, the area we get approaches 1. So what we say is that this integral actually is 1. The area of that blue shaded region that's infinitely wide actually only has an area of 1. And the way you can see this is calculating the area up to different points and taking the limit as the number goes to infinity. Yes, Darryl?
Would the surface area also be a limit or approach a number, or would that be
The surface area meaning the perimeter
if you were to rotate that solid around the x-axis, the surface area?
would actually that's a good question. I'd have to actually do the calculations to figure that one out.
I would think that it wouldn't, or I think it would be infinite.
Yeah, I know for certain this length is infinite.
Okay.
And the question is whether or not this distance approaches infinity faster than the radius of the surface gets smaller. Because as you go farther and farther up, the radius gets smaller and smaller and smaller. I'd have to actually do the calculation to tell you whether the surface area was finite or infinite. And the surface area, yeah.
If they were always the same, or
No, they're not always the same. Yeah, you can come up with things where actually this perimeter, if the width is always infinite, the perimeter will always be infinite. But yeah, the surface area depends what is actually going on. There's really interesting things. You can come up with things that are almost infinite or that are almost finite. There's this weird sort of dividing line that happens. And we'll talk about that a little bit more when we get to section chapter 11 on series. Because series are a little bit, well, they're easier to study, but they require less work to study. They're a bit more, you don't have to worry about all the methods of integration when you're studying them as much. So. Any other questions about the idea? Oh, sorry. I put up this thing on the slide. I haven't said it yet. So the idea is if you see an integral which goes from a number to infinity, you should always think about that infinity really means a number that is going to infinity. So if we see an integral from a number to infinity, what we're really doing is we're doing the limit as t goes to infinity of the integral from that number to t. So if you've got a limit that goes to infinity, what you're really going to do is you're going to replace that limit with the variable t and take the limit as that variable t goes to infinity. That's how you can interpret an area like this. It is a limit of finite areas. And this integral we can do, right? This integral is what I've actually been doing all this time, right? When I did it from 1 to 10, really it would be the same thing, but instead of a 10 here, there'd be a t there. And you can take the limit of that as t goes to infinity. So any question about this idea of making the thing go to infinity before I go on to some more technical details about it? Okay, so in Calculus 1, you've learned the difference between limits that exist and limits that do not exist. Limits that exist are limits that approach some finite number, like limits that approach 2, or limits that approach -6, or limits that approach pi. All those limits exist. Other limits do not exist, and the most common way for limits to not exist is for them to go to infinity or to go to negative infinity. There are other ways for limits to not exist. There can be things that bounce up and down. The limit of that thing doesn't exist as you go out infinitely far. I don't know if you've seen in Calculus 1 if you saw this guy. That goes up and down infinitely often as it goes to 0. This is another example of a limit that does not exist. There's lots of ways in which limits can fail to exist. And if the limit exists, the name we use for that sort of integral is we say that integral converges. or it is convergent. Convergent is just a fancy name for a limit existing. If the limit does not exist, we say it's diverges or is divergent. I don't know why, well, no, I guess we do. I don't know why when they teach limits they don't teach these words. For whatever reasons, when you learn limits, you just learn exists and does not exist. And as soon as it comes to integrals, then you have to learn convergent and divergent. People use convergent and divergent for limits all the time in research level math. They just, for whatever reason, they don't use it in calculus 1 most of the time. But yeah, convergence is just a fancy word for the limit exists. Divergent means it doesn't exist. Oh. But I hit page down or something. Okay. So, if you want to figure out if an improper integral converges or diverges, what you've got to do is you've got to actually write it as a limit, evaluate the integral part of it, and figure out if the limit exists or if the limit does not exist. If the limit converges, the limit exists, and we can find its value. If the limit does not exist, it diverges. That's all you can say about it, is it diverges. So I'm going to do 2 examples here, and I'm going to sort of explain those words convergent and divergent in relation to those 2 examples. So the first example we have is the integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. So the first thing to mention is we have a limit which is infinite. So really what this integral is the limit as t goes to infinity of the integral from 0 to t of 1 over 4th root of 1 plus x dx. Right, that's really what this integral is. Now, some people may be able to see what the antiderivative of this is right off the bat. If you can't see it, you can do it by substitution. I'm going to do it by substitution here just to show you how substitution works when we're using improper integrals. So the substitution we need to do is u equals 1 plus x. If u is 1 plus x, du is just dx. Now, when this happens, when we do that substitution, the 0 gets replaced with 1 plus 0. Because when x is 0, u is 1 plus 0, which is 1. The t gets replaced with 1 plus t. Right? Because you're plugging the t in for x into this formula. So when x is 0, u is 1. When x is t, u is 1 plus t. And basically we're going to have 1 over the 4th root of u. It's the same thing as u to the negative a quarter. When we take the antiderivative of u to the negative a quarter, we get u to the 3/4 over 3/4. Right? You add 1 to the exponent, negative a quarter plus 1 is 3/4. You divide by the new exponent. Now, if we keep going, we want to plug in those limits of integration and subtract. So we'll have 4/3, we're going to have the limit as t goes to infinity is still in front. 4/3 times 1 plus t to the 3/4 minus 4/3 times 1 to the 3/4. Now what we've got to do is we've got to now take the limit as t goes to infinity. So as t goes to infinity, what we really have, 1 plus t is also going to infinity. So what we really have is an infinite number to the 3/4 power. Now, if you remember what happens to infinite numbers, if you take an infinite number to the 1 power, it's still infinite. If you square it, it's going to be even bigger. If you cube it, it's going to be even bigger. If you take its square root, it's 1/2 power, it's still going to be an infinite number. If you take something that's going to infinity, you take its square root, it's still going to become infinite. The only way you can make it not go to infinity is if its power is less than 0. Because if it's a 0 power, it gives you 1. If it's a negative 1 power, it's 1 over infinity, which will go to 0. If you have something to the 3/4 power, it's going to go to infinity. So since this part of the integral goes to infinity, the whole thing goes to infinity. So the integral diverges. So if you have an infinite number to any positive power, it always goes to infinity. And when it goes to infinity, the integral diverges. One thing to mention, in these sorts of problems, I know when people did limits in the past, oftentimes they were required to show a lot of work when doing the limits, to sort of write this as like 1 plus t goes to infinity, therefore 1 plus t to the 3/4 goes to infinity, therefore 4/3 times that thing goes to infinity. I am not going to require nearly as much work when doing these things, as long as you can tell whether the limit is infinite or if it's finite. That's really all that matters here. I don't need to seal your work in doing so. And if you want to figure it out by taking a billion, plug it in for t, see if it gives you a big number or a small number, go for it. You know, like I'm not really testing your ability to evaluate limits using all the technical tools you learned to calculus.
Are you okay with us using like infinity to the power of 3/4?
Yeah.
Okay. Our
Yeah.
Calc 1 teacher did not want us to do that.
Okay, this is a philosophical point for me. I actually believe that infinity is a number, it's just not a real number.
Okay.
So I actually, and this is, again, it's a philosophical point, there's this thing called the hyper-real numbers, which are the real numbers plus the infinite ones and the infinitely small ones. I believe in the hyper-real numbers, so I believe that this is actually this actually means something.
Okay.
But yes, there is. Mathematicians for centuries did not believe infinity was an actual thing, and it actually had, like, historically, it had a lot to do with theology and the fact that if you said that there was a mathematical infinity, that was competing with God.
Yeah.
Like that was the anyways, there's still I'm not trying to say that if you don't like infinities to the 3/4 power, that means you're
certainly
like
a lot
dogmatic,
easier,
like,
but-
anyways.
No, it's better than saying really big.
Yeah, exactly.
Yeah,
That's what we have
exactly.
to do.
Oh, you have to write really big
Really
number to the
big
3/4 equals really big number. Yeah. Now, one thing I will say: use an arrow rather than an equal sign here.
Yes.
I'm not gonna, to be honest, it's not something I'm probably gonna take off marks about. But technically speaking, infinity to 3/4, it does go to infinity. It doesn't really equal anything.
Yeah.
So, yeah. Infinite numbers are directions rather than points, if that makes sense. Okay. So this is an example of an integral that diverges. I'm going to do this second. And if there's anyone else with any other questions about this, feel free to ask them now. Otherwise, I'll move on to the next one. Okay. So the next one is the integral from 1 to infinity of 1 over 2x plus 1 cubed dx. Then the first step is always to take the thing that's infinity, replace it with a t, and take the limit as t goes to infinity. You'll notice the steps in this one very much parallel the steps in the last one. Here, the thing inside the brackets isn't x plus 1, it's 2x plus 1. So my u is 2x plus 1. Annoyingly, here the du is not just dx here, it's going to be 2dx, because the derivative of 2x is 2. When we change the limits of integration, we put, when x is 1, u is going to be 2 times 1 plus 1, which is 3. When x is t, u is going to be 2t plus 1. So here it goes from 3 to 2t plus 1, and this is going to become a u to the 3 on the bottom, which is a u to the negative 3, and it's actually going to be a du over 2 rather than just a du, because du is 2 dx, so dx is du over 2. So the over 2 is a 1/2 that can be pulled up front. Okay, the antiderivative of u to the negative 3. We get u to the negative 2 over negative 2. And that goes from 3 to 2t plus 1. Here, we have, actually, let's put the 2 times the negative 2 gives you a negative 4. Here we're going to have 2t plus 1 to the negative 2 minus 1 over negative 4, 3 to the negative 2. Now in this case, when we put in infinity here, what we get is infinity to the negative 2. Infinity to a negative power is really 1 over infinity to a positive power. Negative 2 is 1 over infinity squared. This thing goes to 0. So really, this whole first term goes to 0, and the second term becomes plus 1/4 times 1/9. So the answer is 1 over 36. So this thing goes to 0, this thing goes to 1 over 36. So here we would say the integral converges. It converges because the limit exists. And what does it converge to? It converges to 1 over 36. Any questions about this example? Okay. So, the other thing we need to deal with sometimes is sometimes rather than having an infinity up here, you might have a negative infinity down here. You might have an integral which involves negative infinity. If you've got an integral involving a negative infinity, what you've got to do is rather than replacing the infinity with a t that goes to infinity, you replace the negative infinity with a t that goes to negative infinity. Negative infinity will always occur on the lower limit. You can never have an integral from something to negative infinity because the upper limit should always be bigger. Yeah. So, to see an example of this, I'm going to do this guy here. Integral from negative infinity to 0 of 2 to the r dr. So the first thing to mention is when we've got to write this thing as a limit. So we replace the negative infinity with a t, and that t is going to go to negative infinity. So, next thing we've got to do is find the antiderivative of 2 to the r. Now, if you remember, the antiderivative of a to the x, the antiderivative of a to the x is a to the x over ln of a. Just because it's the same thing for the derivative of 2 to the r is 2 to the r times ln2, the antiderivative of 2 is 2 to the r over ln2. It's on that first handwriting game of the first class with that list of antiderivatives. So that's your antiderivative. It's got to go from t to 0, and here we're taking the limit as t goes to negative infinity. So I plug in 0, I'll get, oh, sorry. This marker needs to go. So the limit as t goes to negative infinity, that's going to stay in front. When I plug in 0, I have 2 to the 0 over ln2. When I plug in t, I have 2 to the t over ln2. 2 to the 0 is 1. So this first thing is just 1 over ln2. Here, I'm going to have 2 to the negative infinity over ln2. And if we have a number to a negative infinite power, that's going to go to 0. Basically, a number to the negative power is 1 over that thing. If that is 1 over that thing to an infinite power, it's going to go to 0. Now, it turns out if you had a 1/2 to a negative infinite power, that's actually going to go to infinity. One way of thinking about it is, what does the graph of 2 to the x look like? The graph of 2 to the x looks like that. You go up to negative infinity, you go down to 0. One sort of way of checking, what does the actual limit go to? Just go to infinity, go to 0. Pull out your graph and calculate a graph 2 to the negative x, or 2 to the x, and go look at the negative infinity end of it. You'll see that it goes to 0. If it was a 1/2 instead of a 2, the graph would look like this. And if you go to negative infinity, you actually go up to positive infinity. This is what 1/2 to the x would look like. But anyways, if you're having a hard time understanding these infinite limits, your graphing calculator is a great resource for that. So this whole thing goes to 0. So this is just 1 over ln2 minus 0. So the integral converges to 1 over ln2. I'm going to do example 3 and then I'm going to give you the break because that'll actually be the break between the sections. I know the break's a little bit later than it usually is. This is partly because when I paid into lesson time for today, I'd forgotten about the course evaluations. So, yeah. So the next thing we're going to deal with is integrals which go from negative infinity to infinity. You won't have infinity to infinity. Sorry, the first one should be negative infinity. So I've talked about ones that go from a number to infinity. I've talked about ones that go from negative infinity to a number. You can have situations where you have a negative infinity and an infinity on an integral sign. And when you do that, you actually need to split it up into two separate integrals. One that goes from negative infinity to 0, the other one that goes from 0 to infinity. And do each of them separately. And the reason is because each of those parts of the integral is a limit in itself. We don't yet have the notations for writing limit as t goes to infinity, s goes to negative infinity. Like one limit for two different variables. So really split up into two different integrals. Do each of those integrals as a separate limit. One thing to mention is you've got two different integrals. If even one of them diverges, the whole thing diverges. You don't even need to calculate the other one, see if it converges or diverges. If one of them diverges, the whole thing diverges. You don't even need to worry about the other one. If they both converge, that's the only time that the whole thing converges. So here is going to be an example of this. Example 3. This is done. So here we have integral from negative infinity to infinity, x cubed e to the negative x to the 4th dx. So the first thing to mention, I'm going to split this up into two different integrals. One from negative infinity to 0, one from 0 to infinity. Alright, this is totally allowed. Remember, if you want to integrate from a to c, you can integrate from a to b and then from b to c. So for the first one, I'm going to take a limit as t1 goes to negative infinity. Integral from t1 to 0, x cubed e to the negative x to the 4th dx. The second one, I'm going to have a limit as t2 goes to infinity. Integral from 0 to t2, x cubed e to the negative x to the 4th dx. Now, if I want to evaluate either of those integrals, I'm going to need a substitution. And the substitution is that u is going to have to be whatever's in that power here. It's e to the negative x to the 4th. So the substitution we're going to need to use is u equals negative x to the 4th, which means du is the derivative of that, which is negative 4x cubed dx. Now here I don't have negative 4x cubed dx, I just have x cubed dx. So x cubed dx is du over 4. And that's what I'm going to be using when I write out my new integrals. So the first one is going to be limit as t1 goes to infinity, integral from, now when x is t1, u is negative x to the 4th. So this is negative t1 to the 4th. Oh, sorry, this is a negative infinity. t1 is going to negative infinity. t2 is going to infinity. To 0. And this is going to be e to the u du over negative 4. Oh, negative 4. Here. The second one is going to be limit as t2 goes to infinity, integral from 0 to t2 to the 4th, negative t2 to the 4th, e to the u du over negative 4. Again, the substitution works the same in both integrals. What's going to change is the limits of integration. So it's t2 to the 4th there, and it's negative t1 to the 4th. Now, I am going to just work on this second integral. And you'll see why in a second. So if I work on the second integral, I'm going to have, well, the 1 over negative fourth is going to be a constant that comes out front. I'm going to plug in negative t2 to the fourth. So I'll have e to the negative t2 to the fourth minus e to the 0. Plug in the upper limit, plug in the lower limit, subtract. And here I'm taking the limit as t2 goes to infinity. Now what happens is as, oh, shoot, I was supposed to do the, I just double canceled myself. Sorry, I'm going to do the first one. The first one's the one that actually, anyways, I want to do first. I thought I said that way, and then I, yeah, 1 over negative fourth, plug in 0, I have e to the 0 minus e to the negative t1 to the fourth. Oh, no, never mind. That's what's going on. You know what, I put an extra negative sign in, that's what was going on. Anyways, I had this idea that negative infinity to the fourth was a negative number. It turns out it all works out. So here, this thing is e to the negative infinity all to the fourth. A negative number to the fourth power is a positive number. So this is negative of positive infinity. So this is e to the negative infinity, e to the negative power gives you 0. So this whole thing is just 1 over negative 4. Now if we do the second one, the second integral gives you 1 over negative 4, limit as t2 goes to infinity. Here we have e to the negative t2 to the fourth minus e to the 0. If I put an infinity for t2, t2 to the fourth is infinity. So this thing is e to the negative infinity, which goes to 0. So this e to the 0 is just a 1. 1 over negative 4 times negative 1 is 1/4. So the whole integral converges. Both these limits exist, so both these things converge. Since both of them converges, the whole thing converges. It converges to 1 over negative 4 plus 1 over 4, which gives you 0. So this thing converges to 1 over negative 4. This thing converges to 1 over 4. If I add the two things together, I get 0. This whole integral gives you 0. Yeah. So I'm going to hand back the marked quizzes, and then as soon as you get the quizzes back, you can take your break. We'll start again at 1 o'clock exactly. Uh-oh. Did I take the quizzes out of my office or something? I could swear they were in here when I arrived in the classroom. Okay, take a break till 12:57. I'll see if I can find the quizzes before, and I'll give them back after. So yeah, we'll be back at 12:57. I'll get back the quizzes in a second. I think